Hello, this is Lorenzo, a presenter of RTX 3090 team. Our team is ranked at 8th place, and I'm here to share our solution. Prior to begin, I would like to say thank you to the hosts and Kaggle team to have this interesting competition. This is our brief introduction of the competition. In this competition, we are asked to predict two kinds of labels, study level and image level. Study level prediction is to classify what kind of the chest radiograph is, and image level prediction is to localize a bounding box if there is opacity regions. So this is index of this presentation. This is the summary of our solution. We broke down the competitions into 3 tasks: full class classification, opacity bounding box detection, and non-class binary classification. All these tasks are done by assembling different kinds of models with different input sizes. And preprocessing and datasets. Models' performance consistently increased as we increased the input size until 640. Assembling all these sizes gives us further boost. Also, there are some cases that a single study has multiple images. Accepting the recommendation from the host, we remain only one image with bounding box for a single study. Augmentation is one of the keys to improve performance, and we use a NIH chest X-rays dataset for pre-training study level models. And next, training details. Let me begin with study level full class classification models. We train EfficientNet version 2 and SIIM transformer. We cross-validated with stratified group 5 fold. All training epochs are decided by early stocking. Firstly, to train EfficientNet version 2, we use UNet++ segmentation head. Segmentation head outputs 2 classes, opacity bounding box mask and long mask. Opacity bounding box masks are obtained from image level labels, but there are no long masks annotations, so we design a heuristic to obtain long masks. This is done by a series of OpenCV functions and scikit-image functions. Firstly, we apply line histogram equalization to get a cleaner result of thresholding. Thresholding is done with O2 thresholding to segment darker area of chest radiograph. Then we get coarse long masks and other segments, such as background area. To remove background area segments, we use clear border segment function in scikit-image. And to fill the small holes inside of lungs, we reduce the image size very small and enlarge it again. Finally, after removing small segments other than lungs, we get the lung mask. Another study level classification model is SIIM transformer. We pre-trained the model on NIH dataset and it gave much better results than the one trained only with provided dataset in this competition. And we assembled 4 models, UNet++ trained with 2 different image sizes, and NIH pre-trained UNet++ model, and SIIM transformer model. Secondly, image level opacity detection model consists of ensemble of 3 YOLO models with different image sizes and 1 CascadeRCNN model. We use group 5 fold with patient ID, and all folds across different models and image sizes are assembled using weighted box fusion method. We gave more weights to best CV model as twice, and IOU threshold was 0.5. Lastly, image level non-classification models. These models provide the probability of there are no opacity bounding boxes. We thought that knowledge of 4 classification model can help a lot for deciding whether there is an opacity bounding box or not. So we replaced the last linear output layer to have binary output and fine-tune with binary labels whether there is a bounding box or not. The models converged very fast and gave a good result. To prevent potential leak, we used the same validation splits used when training full class classification models. Thank you for listening.